Okay, so I decided I'm going to do organic chemistry. I figure this might be the most applicable for interview who may want to go further in the chemistry. Uh, I know a lot of people they take these chemistry courses because they want to become doctors uh, or do biological research, etc. And you will be taking, you'll have to be taking organic chemistry before you take this class. Now, organic chemistry, when I took it, and probably still today, is known as a killer weeder course. It's one of the most intense courses you can take. Uh, the calculus, physics, and things like that sometimes uh, fall short in terms of comparisons, especially organic too. And part of the problem is that from what I remember is that organic chemistry almost seems completely divorced from general chemistry. You walk in organic chemistry and say, "I never learned any of this in chemistry," and it's supposed to be, and chemistry is supposed to be a prerequisite for it. And so uh, I really wish I'd go back and redo all of it because I know a lot better all that now. Um, but hopefully, some of the stuff that I've gone through in my learning, you guys can help you guys out. But so this is just going to be a brief kind of cover all of organic chemistry. There'll be a lot of stuff here, but maybe what it'll do is just introduce you to organic chemistry and what are some of the things about it. What are some of the things that general chem apply to it? Okay, because like I said, you're gonna walk in if you take organic, you're gonna walk and go, wait a second, what is this? And so and it's almost going to feel like you were supposed to know this stuff before you came in there. So let's just get started, and you're going to see that there's it's organic chemistry is very interesting, and given maybe the right teachers and right circumstances, uh, you'll want to pursue it more. And what I did is that I pursued an avenue of it called biochemistry, and and so so okay so organic chemistry has to do mostly with carbons, hydrocarbons, and so carbon has four bonds, and in Chem 121 we talked about hybrid orbitals and etc. And different types of things, but the carbons have strong bonds and other nonmetals because it's covalent. Uh, it has the capability of forming really long carbon-carbon chains. And with just a simple carbon model, you can form atom. You can form several different, thousands of different kinds of hydrocarbons. Okay, so these are just four of them here, where the black represents carbon and the white represents hydrogen. Now, if you look at the shape here, it sort of gives you the three-dimensional shape. And if you remember, you have when you have four connections to one atom, it's called tetrahedral. Okay, so you can see this is a single bonded. All the carbons are single bonded here. We'll see that this is a type of carbon compound called alkane, which is a saturated hydrocarbon, which means there's nothing but single bonds between the carbons. Same thing here. But the difference between these two is you can see that the 1, 2, 3, 4, the 1, 2, 3, 4 is that they both have the same chemical formula, C4H10. The difference is that so these guys are called isomers, which means they're the same but different, and their same chemical formula different because they have a different chemical bonding. And same thing goes here. So this guy would be known as 1, 3, 4 butane. And if you took 121 from me, you would know that. And this one is 1, 2, 3, 4, but it's not a butane because this is butane. This has a different structure. This one is called 2-methylpropane. And we'll go over a little bit about that. And so there'll be naming procedures to coming up with and naming carbon compounds in organic chemistry. So this one down here is C2H6O. The red is oxygen, and so is this. Looks like a little doggy here. So they're isomers of each other, and you can see they're different. Now, the way that this guy oxygen here makes it so when we talk about carbon compounds, we'll start out with just all carbons and hydrogens, and then what we'll do is we'll add oxygens, and these are the things will be called functional groups. So this guy we'll find out is dimethyl ether, and this one here is ethanol. Okay, so how can you tell that by looking at, well, the thing that determinants is this oxygen here. When oxygen is between carbons, it's an ether, and when it's at the end with a H, it's an alcohol, and we have a special name for those. And again, if you took Chem 121, 2 carbon is F, like ethane, so this is ethane, and when it has this group here, it's an alcohol, so we say OL, so it's ethanol. And I'll go over some of that down the road, and we won't go into the same kind of intensity you would get organic chemistry, but it'll expose you to some of the kinds of things you'll hear. All right, so pentane we learned with C5H12. So, and this is one way to draw it. Okay, maybe called Lewis structure, bonding structure. Notice it's drawn in a way that might represent its tetrahedral shape with the angles. Okay, so each carbon has 4 bonds, and all of the bonds are single. So we're going to learn that anytime you have all carbons and all single bonds, it's alkane. Okay, and we call it the Lewis dot structure. The condense formula gets rid of all the bonds and just shows the bonding, who's bonded to who. Okay, CH3 means there's 3 H's attached to the carbon, and so forth like that. So as I just said, so this is what we call Lewis structure of pentan 1-ol. So this is a 5-carbon chain, pentane. It has this OH in the end, so it's alcohol. So we will have it end with OL. And what carbon comes off will determine how we number it. And so the way we're going to number it is we will number it determining the carbon closest to the alcohol. We'll number it from. So if we name it down here, it'd be 1, 2, 3, 4, 5 penta 5-ol. But we like to have the number smaller, so it'd be penta 1-ol. Now another way you can do it is just write this out like this, get rid of all the bonds, and it's also known as 1-pentanol. Either one will do in terms of way you'll learn it. Now, depending on your class, they'll ask you to learn it one way versus the other. But notice there's OL, 1, and pent. Now, one of the things that's really important in organic chemistry is the 3-dimensional structure of molecules. And when we draw three-dimensional structures on 2 dimensions, we lose a lot of information. First of all, this is a tetrahedral shape, but you can't tell that by the way it's bonded. Here it looks like a cross. But if you remember from 121, this actually looks like a tripod with, a hydrogen sticking off the top. Okay. Now the other thing about this is, so the name of this guy is going to be, let's see, 1-bromo 1-chloroethane. Okay, so this guy over here is the same thing. So this is the first carbon. 1-bromo 1-chloro. Do it alphabetical. So 1 coming, bromine's coming off number 1. 1-bromo 1-chloro, and this is ethane. So it's 1-bromo 1-chloroethane. Okay, this is number 1. It has a bromo S, so it's 1-bro. So you might think that these are the same. Okay, but if you looked at these two guys, if you were to actually look at their three-dimensional structures, what you would see is that they're not identical. You would find that they're actually mirror images of each other, and just like your left hand and your right hand don't fit right on top of each other, these guys are mirror images of each other. Okay, and we won't go more into that now, but if you take organic chemistry, you'll see that's a really important thing, especially in terms of like, all over the place. But one place I used to use it, use it in biochemistry, is in amino acids and carbohydrates. Okay, here's another example of it. Now, and we're not going to get, so this guy is a mirror image of this, and the key way that you can tell is that what you do is you pick out one of the carbons, and if it has 4 different things attached to it, so this carbon has oxygen, has this group, this group, this group, and this group, so that means it will have a mirror image. Okay, so, and it's called a chiral carbon. And that's all you need to know for now. All right, chemists, just like everybody else in the world, are lazy, and so instead of writing out all these carbons and hydrogens and so forth, we have a short way to do that, and we can just get rid of the carbons and hydrogens and just have a write out line formula where the points represent the carbons. Now what it's assumed is that the line is a carbon-carbon bond, and every other bond that's not shown will be a carbon bond. A carbon-hydrogen bond. So this carbon, 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 and every carbon has 4 bonds, so there'll be 3 coming off here, 2 here, and 3 here. So that's the kind of thing you pick up on. So this guy here, it's an alcohol because it has an OH at the end, so it'll end in OL. 1, 2, 3, propanol, or propan-1-ol, it might be called. If you write it in the line formula, it says 1, 2, 3, 4. 1, 2, 3, 1, 2, 3 connections, and it has a oxygen coming off of it, and so this represents this molecule right here. Okay, so here's butane. Butane has, remember, methyl, ethyl, there's methane, ethane, propane, butane. Meat eaters prefer beef. So this has 4 carbons, 1, 2, 3, 4. Butanol would have 1, 2, 3, 4, and OH coming off the end. Okay. So now these are called ring structures, and so there's carbon here, carbon here, carbon here, carbon here, carbon here. Then there's 2 H's coming off of each one. Okay. And so instead of writing all those carbon hydrogens, we just write this symbol here, and that name is cyclohexane. The reason why it's called cyclo, because it's like a ring. It's a hexane because it has 6 carbons in it. Now, when you take organic chemistry, you'll learn that its 3-dimensional structure isn't flat like this. It ends up being kind of a bent structure, okay? And so you learn about the boat and the chair for conformations of cyclohexane, which is, I thought, was one of the most interesting things that really got me interested in chemistry, was the different, how molecules can change their shapes and still be the same molecule. All right, cyclopropane. So this is C. So this is an alkane. An alkane has all carbons and hydrogens, all single bonds. Because it has a ring, it's called a cycloalkane. Okay, the formula for alkanes, that's the long chains without the ring structures, are always going to be CN H2N plus 2. So that means, or N equals the number of carbons. So if you have 5 carbons, the number of hydrogens would be 5 times 2 plus 2. And that's the alkanes. That's the straight chains. Okay. The cycloalkanes are simply going to be a CnH2n. So the number of hydrogen here is twice the number of carbons. So this is C6H12. This is C3H6. Okay, each carbon, and there's 2 coming off. That's why there's twice as many. Okay. And then this guy over here is a special case. It's called benzene. They named it before they knew what the structure was. It has an interesting history on how the fellow that came up with the formula. The structure. It's got double bonds in it, and so it's not an alkane. It's like an alkene, which we'll learn about in a minute. But it's neither of the. It's not that either. What benzene has, it's called aromatic, and aromatic means it has resonance, and that means, as we learn in 121, is that the double bonds can move around, and when the double bonds move around, what they do is they stabilize the structure. The double bonds each, remember, the double bond is made out of sigma bond and a pi bond. And so you have pi bond here, pi bond here, pi bond here. And what they do is they flip around, and actually they don't do that at all. It's actually they mix as just one giant bond that floats above and below the molecule. And this molecule is indeed flat. It's one of the most interesting molecules there is out there. Okay. All right, and then what we have is these things called heterocyclic, and that means where they have besides carbons in the ring structures, they'll have another element like nitrogen or oxygen. Now, you don't have to know the names of these, but one of the things that a lot of times you'll run into these when you get an organic, but the pyridines, pyrosols, you'll see structures like this. If you get into drug design, you'll see a lot of drugs are made, pharmaceutical drugs are made with these components. Okay, so these are all really important in terms of pharmaceutical studies and biochemistry. Okay, draw at least 2 geometric structures with C4H10. Okay, so what you have here is you have 4 carbons. So when you see the carbons here, connect to 4 carbons. and then connect them any way you can. So you can connect them straight across, or you can connect them like this. And so you have two different ranges. So these guys are isomers of each other, geometric because they have different shapes. Different bonding. And this guy would be called butane, 1, 2, 3, 4. And again, this would be 1, 2, 3. So it would be a propane with a methyl coming off of number 2. So this would be 2-methyl propane. All right, now to the alkanes, the hydrocarbon chains, what you can do is you can add oxygens or nitrogens to them. And when you do that, you have different kinds of groups you can add them, and they're called functional groups. So if you add OH to a carbon group, that's what the R stands for. It's called alcohol, and this OH is called a hydroxyl. If you add a COOH, this is called carboxylic acid, and we'll get into that a little bit. To a carbon group, it's an acid or carboxylic acid. And if you put an oxygen between two carbon groups, it's called ether. Now there's more of these functional groups. There will be aldehydes, ketones, amines, esters, amides, and probably I can't remember other ones as well with sulfur and phosphorus. Okay, so here's a group. Here's a table of functional groups. So you have your hydrocarbons. Your most basic is the alkanes with nothing but carbons on them. Hydrogen and carbon. If you have at least one double bond, it's called alkene. If you have a triple bond, replacing one with a single bond, it's called alkyne. These guys are called, alkanes are called saturated because they have all single bonds. If there's at least one double bond or one triple bond, it's called unsaturated hydrocarbon. And then you have the aromatics, like benzene. You have your alcohols, which have OH. You have ethers, where you have the O in the middle. You have your aldehyde, which has this double bond oxygen at the end of a carbon chain. You have a ketone, where you have the double bond stuck in the middle. It's not at the end. You have a carboxylic acid, which looks a little bit like the aldehyde and the alcohol together. Carboxylic acid. There's ester, which instead of looks like a carboxylic acid but still having an H at the end, has a carbon. And then there's amines, which are carbon groups that have nitrogens attached to it. And then there's amides, which have a carboxylic acid attached to an amine. And these are found in proteins. So places, alcohols, there's ethanol is the thing that, is booze, and then there's other times that all kinds of different kinds of alcohols. There's aldehydes, you've probably heard of formaldehyde, ketones, everybody's probably heard about ketone bodies and keto diet. Carboxylic acids are fatty acids, amino acids. Esters are triglycerides, you find them called triglycerides, amines, amino acids, nucleic acids, amides, found proteins. So, I run through that and just giving you a background of some things you may have heard and seen with these. Okay, so looking back at the previous table, I want to know which one of these is ester. So ester has oxygen is going to be D, okay? The way that it works, it has an oxygen and it has two oxygens in the chain. Okay, this one will be a carboxylic acid. Okay, this is going to be a ketone. because it has a double bond of oxygen between carbons. And this is like a combination of these two here, where it has an oxygen, has this thing up here, but it replaces this group, this OH here, it replaces this H. So this is a carboxylic acid. Ester is just like a carboxylic acid, but instead of having H, it'll have a carbon group. Okay, hydrocarbons are molecules that just have carbons and hydrogens. And I just said you have alkanes, which are all single bonded. Like the chemical formula is CN, H2N plus 2. And then you have alkenes. If it only has one double bond, the formula will be CN, H2N. And don't worry about these things here. But notice the names is that if you have an alkane that ends in ane, if you have an alkene that ends in ene, if you have an alkyne and it ends in ine. And then aromatics like benzene will have their own special naming and so forth. All right, hydrocarbons. Alkanes are defined as saturated carbons. That means they have all single bond carbons. Means you can't add any more hydrogens. Alkenes and alkynes are unsaturated. That means they have at least one double bond. That means you can replace one of the bonds in a double bond with hydrogens to make it saturated. Alkynes have triple bonds, so you can replace two of the bonds with hydrogens. So an example that we'll go over is that you can convert an alkene, or unsaturated hydrocarbon into a saturated hydrocarbon by adding hydrogen and replacing the double bonds. Okay, and this would be called reduction because you're adding electrons. Hydrogens is electrons, so you're reducing this double bonds, and you're forming the alkane. So one of the things is when you add hydrogen, remember oxidation reduction. When you oxidation is when you remove electrons, and reduction is when you add electrons. Well, hydrogen, you can think of it as are electrons and protons. And when you add this hydrogen, really what you're doing is you're adding its one electron. So essentially when you add H2, it becomes you're reducing. So that's one of the things you'll see in organic chemistry, biochemistry. You'll see a lot of times that H2 is added to a chemical and they say it's reduced. And what it means is that the electrons of the hydrogen are being added to the bond, to the carbons or whatever. Okay, aromaticity. Okay, so it can characterized by conjugated bonds in a ring such as benzene. Conjugated bonds means double bonds. Pi electrons delocalize over the ring. Now in 121 we learned that if you could spread out pi electrons, you could stabilize them. And that's what happens in these structures like benzene. What happens is these pi bonds, pi electrons in the pi bonds, what they could do is they could spread out over this whole structure and become essentially flatten out and are really hard to be found. And so these conjugate structures, they stabilize these pi bonds, and so this is a really efficient way to store electrons. is on a conjugated bond system. This guy's a great guy for stabilized electrons because his electrons can be shared over those pi electrons that would, if you just cut this thing out and put it all by itself, those pi electrons would be snapped up by some electronegative atom. But now, when they're here, they can be spread out this whole structure, and essentially it lowers the charge density of the pi electrons and making them basically very, very stable. Okay, so naming hydrocarbons. Okay, so and I was kind of just saying this a little bit previously, but we'll go over a little bit of how to name these, because when you get into organic chemistry, you'll spend your first couple weeks just learning how to name all these kinds of different molecules in all their different ways. So let's just go over them. So what you're going to do is that if it's all single bonds, hydrocarbon, it's going to be alkane and an ane. And then what you're going to do is you're going to find the longest chain, and you're going to call it, you can name it according to that. And then you're going to have side groups coming off of it, and then you're going to name it according to that. Okay, and this is one thing I had you learn in 121 was all these guys. Okay. Right now, so what you're going to do is you're going to have a long chain of carbons, and then you're going to have side groups hanging off the side. And those side groups will be called alkyl groups. So, for instance, you'll have a long carbon chain with this CH3 coming off the end. And because it's one carbon, it's going to be like methane, but you're going to get rid of the ane and call it YL or methyl. If it was two carbon group coming off, then it would be called an ethyl. 3 group, it would be propyl, so forth, probutyl, and so forth. So, okay. Right, so let's take a look at this guy. So this guy is oh, there should be a carbon right here. So 1, 2, 3. Oh, no, these are the same. Okay, so this is a propane here, and propane. All right. So let's see how to name this guy right here. So this guy is, first of all, you find the longest chain. So the longest chain is 1, 2, 3, 4. 1, 2, 3, 4. Okay, so there's more than one way you can get the longest chain. It doesn't have to be all in straight. It could be bent 1, 2, 3, 4. So I'm going to, and they'll give the same name in the long run. So you got 1, 2, 3, 4. So this is going to be a butane. Okay, and it has this CH3 coming off of it. So this is a methyl. So this is going to be a methylbutane. Okay. So the other thing is you want to tell what carbon that comes off of. So you have to number the carbons, and there's 2 different ways you can number the carbons. You could number 1, 2. So if you went from left to right, it'd be 2-methyl butane, or if you went from right to left, it'd be 3. You pick the number that gives you the smallest. So if you go this way, it'd be 3, this way 2. So you're going to call it 2-methyl butane. Okay. So 2-methyl butane. All right. How about naming this guy right here? So what you do is you find the longest chain. 1, 2, 3, 4, 5. Is there any other way you could do it? 1, 2, 3, 4. 1, 2, 3, 4, 5. So the longest chain you can get is 5. You can get it this way, or you can get it this way. So it's going to be a pentane. 1, 2, 3, 4, 5. Okay, so this is the chain, pentane, and it has a methyl and a methyl coming off of it. Okay, so we have to number them. So if we go from left to right, it'd be 1 methyl, 2 methyl. If we went from right to left, it'd be 3 methyl, 4 methyl. Okay, so we know left to right is the best one. Now the one thing about, so we might think it's 1 methyl, 2 methyl pentane. Okay, but what you do is when the same group, alkyl group, shows up, well, you just use di or tri to shorten it. So this is going to be 1, so it's going to be 2, 3 dimethyl pentane. Okay, so you don't have to say methyl twice. So you'll say 2, 3 dimethyl pentane. Okay, so you count them. So it comes off 2 and 3 methyl groups, and then you get 2, 3 dimethyl. All right. So let's consider this one. All right. Okay. So notice it's not a straight chain, so you have to figure out the longest chain. So my guess, I'm going to start here. 1, 2, 3, 4, 5, 6. Now, is there another chain that'd be longer? 1, 2, 3, 4, 5. Okay, no, I think this is the longest chain. 1, 2, 3, 4, 5, 6. So this guy's the longest chain, so it's hexane. Okay, that means it has this group and this group coming off it. This is a methyl, and this is an ethyl. Right, the numbering is going to be 1, 2, 3, 4 from right to left, or 1, 2, 3. So we're going to go this way. So it's going to be a 3 methyl and a 3 ethyl, and a 1, 2, 3, 4, 5 hexane. So you have 3 methyl, 3 ethyl hexane. Now, what you have to be careful about here is, who do you put first, the methyl or the ethyl? Well, it goes alphabetical. So it's going to be ethyl before methyl. So this is going to be 3 ethyl, 3 methyl hexane. Comes off number 3, so you have your ethyl and you have your methyl. So it's going to be 3 ethyl, 3 methyl hexane. 3 ethyl, 3 methyl hexane. And this is sort of what it looks like in 3D. All right, how about this one? Okay, so find the longest chain. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So I think the longest chain will be 7. Usually, if you can get the numbering more than one way, it won't matter which way you name it. It'll give which way you go to get the name. It doesn't matter if you go this way or this way. It'll probably give you the same name. So I'm just going to go straight across. So this 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7. So this is heptane. Has ethyl coming off of it. It comes off of number 3 going left to right. Number 4 going right to left. So I'm going to go left to right. Just give me my numbers smaller. So this is going to be 3 ethyl heptane. All right, number C, right there. Okay, how about this guy? Again, find the longest chain. 1, 2, 3, 4, 5, 6, 7, 8. So it's going to be octane. Okay, it has 2 ethyls coming off of number 3. 2 methyls. So if you go right, it's going to give you smaller going left to right and right to left. So it's going to be 3 3. So you don't say 3 methyl 3 methyl. You say 3 dimethyl octane. So B. All right, alkanes, chemical properties. They're pretty stable. Almost just about anything you add to them is going to be really hard to interact. But what you can do is you can combust them with oxygen to form carbon dioxide and carbon monoxide. They're basically the most reduced form of carbons, and the most reduced form is usually the most stabilized. Okay. All right, you have alkenes and alkynes. Alkenes contain more than one or more double bonds. Okay, this guy is ethene, has a 2-carbon alkene. There's no such thing as a 1-carbon alkene because you need at least 2 carbons to make a double bond. So this is the smallest alkene. It's also known as ethylene. And then this is example of an alkyne. And this guy, it would be ethyne because it has 2 carbons. And its common name is acetylene. They're nonpolar. Okay, we covered this in 121. If you have a lot of carbons, they're very nonpolar. In fact, all hydrocarbons are very, very nonpolar. These will react fairly well because of the double bond. One of the bonds is pi. In the case of the alkyne, you have 2 pi bonds, and they're very reactive. Okay, naming. So in terms of the alkenes, you'll end up with ene. And if you have a triple bond, you have ine. Okay, so let's name alkene. So you have 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So this is going to be a heptene. Okay, now it has a double bond coming off right here. Now what you want to do is you want a number that gives you the smallest, that gives after the what a double bond comes off. So if you go from left to right, it's 1, 2, 3, 4, 5 would be 5 heptene. Okay, if you go from right to left, it's 2. So the way we name it is, there's 2 different ways you kind of can name it. You can name it 2-heptene, or you can write it as hep-2ene. Sounds like something out of Star Wars. Okay. All right, so this guy right here has 1, 2, 3, 4 carbons is the longest chain, and it doesn't matter how you go there. You get it this way, this way, this way, and so forth. The double bond comes off number 2 no matter which way you go. And it has 2 methyls. So this guy is going to be a 2, 3 dimethyl 2 butene. Okay, so it's 2, 3 dimethyl butene, right? So again, you don't say the methyl twice, and you can either say 2, 3 dimethyl 2 butene or 2, 3 dimethyl butene. Okay, polyenes. Okay, that means a lot of carbons on them. Okay, so this guy here, it has more than one double bond. So you have, it's 1, 2, 3, 4, 5, 6. You want to number it according to where you put the double bonds, giving the lowest numbers. So you can have a double bond coming off number 1 and number 3. So this is 1, 2, 3, 4, 5, 6. And it has 3 double bonds, so it'll be hex, the longest chain. It has double bond coming off of number 1, 3, and 5, and there's 3 of them, so it's triene. I'm sorry, the last one was 1 hex 1,3 diene. This one is hex 1,3 triene for the same reason. Okay, cyclic alkenes. Okay, so again, the way that you're gonna start numbering them is you're gonna start numbering from the double bond. So let's say you have this. So these are methyl groups coming off of here. So this would be number 1. Okay, so trying to see if this is actually right. All right, we'll just go with it. So this says it's carbon 1, 2, 3, 4, 5, 6. So this would be 1 methyl. 1,6-dimethyl cyclo 2-ene. 1-ene. Other examples of cyclo alkenes are cyclic alkenes are these guys here. All right, how about this one? Okay, so so this is going to be cyclopentane. Okay, so all these and it's going to come off of number 1. So all of these have got 1. Okay, it has 2 methyls coming off of. No, coming off 1, 2, 3, 4, or if you're going the other way, 1, 2, 3. So you want to go this way, okay, because that way it's 1, 2. So if you went this way, the double bond would be coming off of number 5. Okay, so we're going to go clockwise. So number 1, 2, 3, 4. So it's going to be 1, 4 dimethyl cyclopentane. All right, what is the correct structure for 3,3-dimethylpro-1-ene? Okay, so all of these are, well, this is a propane, or this is a cyclopropane. Okay, all right, so this is the wrong name. It should be cyclo in here. Cycloproene. Okay, so so which one is it? Actually, none of them. All right, because this would be a long chain. But if we had cycloproene, then so we want to find, so which one has, so number 1. So this one, so let's take a look at this guy. Carbon number 1, 2, 3. So it's C. Okay. So 1, 2, 3. So number 1 has a double bond to, okay, or we could go the other way. It gives you the same thing. So this one is going to be cyclo. This is going to be 1, 1 cyclopropane. Okay, so this one, you number it, doesn't have a double bond in it. So what you do is you number it according to giving the smallest number for this alkyl groups. So this has 2 methyls, and it's got, if you put them there, if you start anywhere else, it won't be the smallest number. So we'll say this is carbon number 1. So this would be 1, 1 dimethyl cyclopropane. Right. This is a propene, cyclopropene. So starting here is probably your best spot. So it's 1. So you have a 1 dimethyl cyclopro-1-pene. So that's a 1. Right. As we said, this is, if you start either spot, this would be, if you start here, it'll be 1, 2, 3. So it'll be 3,3-dimethyl cyclopro-1-pene. All right. This one, it'll be 1, 2, 3, 4. So it'll be a 2,3-dimethyl, so forth. All right. Okay. So when you have a double bond, with the double bond, if you have single bonds, what you can do is that things can flip around, and really the best way to do this is get a model, and with like the models I show you in class. And with single bonds, what you can do is you can rotate around the bond, so this Br could rotate down here, and so forth. But with a double bond, what it's like, I think I showed you, it's like having two springs, and what that does is it locks this bond into place, so you can't rotate. So you can't rotate around a double bond. So this structure and this structure here are different, even though they have the same. If you just looked at them, you would say they're 1,2-dibromoethene. Okay, so because they both have 2 bromos on them, and they both come off in 1 and 2. But the problem is that you can't. They're not the same structures, because this guy has Br on this side and Br over here, and this one has on the same side. So what you have to do is name them according to where these groups come off. Now, if the groups are opposite of the double bond, we call that trans. Trans means across. Okay, if they're on the same side, it's called cis. Now, you've probably heard, I know you've heard cis and trans in terms of all that crazy stuff these days, but place you'll hear is also like trans fats and cis fats. Okay, and trans fats will have a situation like this, where we'll have a double bond in groups opposite each other, and cis fats will have groups on the same side of each other. Okay, one of the things about alkenes is how they react. You can, like I said, the double bond could be, the pi bond could be broken by adding hydrogens or some other highly electronegative ion, because what the high electronegative atom will do is come and rip the electrons off and actually attach. So hydrogen is fairly electronegativity, and so what it can do is attach itself, and it's called hydrogenation. You can add hydrochloric acid, and so both the hydrogen and the chlorine will attach. You can add water, and this is called hydration, because you're adding water, and OH and H will bond to this guy, and then Cl2. Okay. And when you get into organic chemistry, you'll talk about how these happen. Basically what it is a pi bond is being replaced with a bond from another by attaching another bond. Okay, so this lecture is going to be kind of long. So I'll tell you how I'll break it up, so you don't have to listen to the whole thing at once. But I'm just going to plow through it, and you can listen at break it up into segments. Okay, now we're going to talk about aromatic hydrocarbons. And so there's nothing but hydrogens and carbons, and what they'll have is these double bonds. And these double bonds are situated like in benzene. So, and remember, double bonds have pi bonds. Pi bonds. And the pi bonds are usually unstable, but if they can delocalize or spread out, they become stable. In a benzene structure, the pi electrons become very stable because they can be spread out, reducing their charge density. And this is a really good way of storing, stabilizing electrons. It really is that the chemical formula looks like when you get this structure, when you actually look at the actual model, the actual structure, you really can't find the electrons. And what they're doing, there's there's 3 electrons above and below the plane shared in the pi bond. So what happens is that they're not stuck in a single pi bond. They actually spread out over the whole molecule. And it's actually not 3 bonds, it's actually 1 bond. And so it delocalizes the bond, which is the resonance stabilization that we talked about with resonance. Okay. Now, even though these pi electrons are very stable, you can have them react, and what you need is a highly electronegative atom like chlorine. And if you do it in the presence of ferric chloride, and we won't talk about that, what you can do is you can have the chlorine add to and replace a double bond like this. Okay, well, it doesn't replace it. Actually, it just replaces the H. So you don't lose. So what you get here is what we call a substitution. And what that means is you're substituting a hydrogen and not actually the double bond. So you're not losing the resonance structure reactions. Okay, so in substitution reactions, you maintain the resonance structure because you're substituting for a hydrogen. But we'll see in a minute. You have these other thing called addition reactions, which are going to be you're going to be adding the chlorine and breaking the bond like in hydrogenation. Okay. So substitution means when you substitute a hydrogen without breaking the double bonds, and you'll get, like I said, when you get in organic chemistry, you'll spend more time on that. Addition is where, in this case, chlorine is added to the ring, and it breaks, and the double bond, one of the double bonds disappears. And what that does is it breaks down the resonance structure. Okay, and so now these pi electrons are much more unstable, and they can be reacted well. So a lot of times, what you want to do in organic chemistry is you want to destabilize pi bonds like this. And so first thing you do is you add something like chlorine to destabilize this overall structure. And then once you do that, now the pi bonds become more exposed. Okay, and then what you can do is you can do further reactions with it. Okay, so what product would form if benzene reacted with nitric acid using appropriate catalyst? And we're going to assume that this is, so this is going to be a substitution reaction. And, okay, and that's because of the acid. The acid is going to push this reaction. And so what happens is nitrate adds on, removes the double bond, forms the nitrite on it. So you're breaking the double bond, so it's a substitution. Okay. All right. So usually, so if you're just getting acid and so actually all four of these reactions will take place, but the first one will take place, and probably the most abundant will be just adding this here. And okay, so let's just skip over that. It gets a little more complicated than this, writing these things down. All right, so now let's talk about organic compounds containing oxygen. So far we've just been talking about hydrocarbons, but now we're going to add oxygens to the hydrocarbons, and these will come in the form as functional groups. Okay, so if you add an OH, and this OH is called a hydroxyl, to your carbon group, the molecule becomes alcohol. If you add oxygen between two carbons, it comes ether. If you add a double bonded oxygen at the end of a molecule, it's called aldehyde. If you add a double bonded oxygen between carbons, it's called a ketone. If you add a double bond and a hydroxide, so these are this is called a carbonyl. These double bonded oxygens. So carbonyl at the end is called aldehyde carbonyl, and that's CARBONYL. When you add it between carbons, it's called a ketone. When you add it with a hydroxyl, it's called a carboxylic acid. And when you take carboxylic acid and replace the R with another carbon group, it becomes an ester. So these are the six main functional groups we call. Now, if you look, there's relationship. Alcohol and ethers kind of look alike. Is that they both have RO and then H, RO, or R. Okay, aldehydes and ketones are alike. They have R carbonyl, R carbonyl hydrogen. So you can kind of, and then you have carboxylic acid, which is carbonyl hydroxide, H. And then you have carbonyl oxygen carbon. So you have actually three groups. You have the alcohol ether group, you have the aldehyde ketone group, and then you have the carboxylic acid ester group. And each group, what makes difference is what's attached at the end, as H or a carbon group. All right, so we'll go over alcohols first and ethers, so they're in common. Common alcohols end in OL, like methanol. If it's two carbons, it's ethanol. If it's three carbons, then depending on where the OH comes off, it's going to be propanol, propan 1-ol or 1-propanol. There's two different places you could have that OH come. You could have it off the end at the beginning. If it comes off at the middle, then it would become a propan 2-ol. Alcohols form hydrogen bonds. Hydrogen bonds are special kinds of dipoles, which they form with water and other alcohols. And it's not a bond. It's a molecular interaction between other molecules, and it really stabilizes the molecular interactions. And so, so one of the things is alcohol is very so it has a higher boiling point than predicted because it can form these hydrogen bonds. Okay, there's three different types of alcohols depending on where the hydroxyl comes off. So OH is called a hydroxyl. So if you look at the carbon that has a hydroxyl coming off it, if it only has one carbon group, R means some carbon group, then it's primary alcohol. If the carbon with the hydroxyl has two carbons coming off of it, it's secondary. And if the carbon with the hydroxyl has 3 carbons off of it, called tertiary. Okay, ethers are when you can replace the H with a carbon group. So so what we're going to do is we get rid of the H and we add a CH3. So the way that you name these is, first of all, you notice that it's an ether because it has an oxygen in between. And then what you do is you name according to what things are attached to the oxygen. So this has a methyl and a methyl, so it's dimethyl ether. Okay, this has ethyl and ethyl coming off of oxygen, so dimethyl ether. This one has a methyl and ethyl, so it's going to be, and they got the names backwards here, this should be ethyl methyl ether. Okay, so you name it alphabetical. Right, these won't form hydrogen bonds, so they tend to be evaporate fairly quickly. Have a lower boiling point, are easier to evaporate. They have they're fairly volatile. That what we learned in at the beginning of the semester about volatile solutions. They're not very reactive because that oxygen is really kind of locked in place. All right, reactions of alcohols. Alcohols can undergo oxidation. Okay, and what that means is removing. So reduction meant to add hydrogens, oxygen to oxidizing instead of adding hydrogens would be removing hydrogens. So what you can do with alcohol is you can oxidize it, knock off 2 hydrogens, and when you do that, you can form an aldehyde. And then what you can do, you can further oxidize this by adding oxygen and turning it into a carboxylic acid. So adding hydrogens would be reducing, being reduced. So this guy is being oxidized. Okay, so aldehydes are more readily oxidized than alcohols. So like I said, you can take the aldehyde after you oxidize the ethanol, and then you can oxidize it. Instead of taking away hydrogens, you add oxygen. So there's 2 ways you can oxidize. One way is to remove hydrogens, and the other way is to add oxygens. So if you add an oxygen here, this becomes carboxylic acid. Okay, so with the primary alcohol, what you can do is you can reduce it, you can oxidize to aldehyde and further to a carboxylic acid. Secondary alcohols, you can knock off 2 H's, okay, just like we did before. So in the previous slide, we had a primary alcohol. You knocked off 2 H's, and you ended up with an aldehyde. Okay. Now, if you have a secondary alcohol, what you can do is you knock 2 H's, one here, and then you'll end up with a ketone, where this oxygen is in between these 2 carbon groups. And you can't do anything more with them. Okay, you can't oxidize because there's no end on them. Okay. Tertiary alcohols, the ones with 3 carbons, they can't be oxidized because they don't have an H on the, they don't have 2 hydrogens to knock off. They only have 1. So primary and secondary alcohols you can oxidize. You can oxidize primaries to aldehydes, and you can oxidize secondaries, the ketones. And then you can further oxidize aldehydes to carboxylic acid and oxygen. Okay, so you can also dehydrate alcohols, and that means you can knock off waters. And so, okay, and there's a process of doing this, and you'll learn more about this in organic chemistry. But basically, it's the, I mean, we do the opposite reaction, going right to left. That was called hydration. So you can take water, add it to a double bond, and form an alcohol. You can do the reverse reaction, where you can actually knock off the oxygen, the hydroxyl and hydrogen, to get your alkene back. And we won't get into this, okay? And this is all the fun stuff that you learn in organic chemistry and why it happens. Okay, you get moving around of bonds and electrons, and then you try to figure things out, how things connect. And you get these arrows, and you try to move the arrows around. Okay, so substitution means you can replace a group with some other, so like halogen, and so you have your acid, and then you add it to your alcohol. What you end up doing is removing water, but you end up adding your halogen. Okay, and again, there's a lot of information here. So like water leaves, and the halogen ion attaches the carbon site. And so there's a whole mechanism here. So like what the first thing that happens is this H attaches to this O, and that ends up making this OH2 plus, which is, and then the bromine comes in and attacks it, knocks off the OH, and you end up with this. So this is, I mean, the steps are really kind of interesting how this all takes place. Okay, aldehydes and ketones. So this is another group where you have the carbonyls, and you can have a carbonyl at the end. You have the carbonyl between. If it's at the end, it's called aldehyde. If it's in between, it's a ketone. All right. Like alcohols end in OL, the aldehydes will end in AL. The ketones will end in ON. So let's look at naming an aldehyde. Okay, so what you do is find the longest chain. 1, 2, 3, 4, 5. You always start with the end that has the carbonyl. So this is going to be this number 1 carbon. So it's be 1, 2, 3, 4. So it's going to be 1, 2, 3, 4, 5. So it's a pentanal, and it has a methyl coming off of number 3. Okay, let's try this one. So this is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 6. So it's hexanol going this way or going this way. It has ethyl coming off of number 4. So you're always going to start with the end of the aldehyde. So it's going to be 4-ethyl hexanol. Right, naming ketones. You're going to use ON at the end. Okay. So you find the longest chain. 1, 2, 3, 4, 6, 7. So it's going to be a heptanone. Okay, so what you want to do is, now this one, you decide where you're going to start. So you'll start from this end. It'll give you the smallest number. So it's going to be 3, and there'll be a an ethyl group coming off of number 4. So it's 4 ethyl, 3 heptanone, or 4 ethyl hepta 3 one. Okay. It's the longest chain. Okay. The carbonyl comes off number 3. So 3. And it has ethyl coming off number 4. All right, your turn. Okay, so this is going to be an aldehyde, okay, because it has the carbonyl at the end. And so you number it from this end. You don't have to figure it out because it always starts at the end for aldehydes. So it's 1, 2, 3, 4, 5. So it's going to be a pentanol, 1, 2, 3, 4, 5. So it's going to be one of these A, B, or a D. And it has the methyl coming off at number 2, 2, 3, 2, and 4. So it's going to be 2,4-dimethyl. And you don't have to say 1 because it always comes off of the first. So it's simply 2,4-dimethyl pentanol. Right, ketones. Okay. Find the longest chain. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Now you might find a chain that's longer. 1, 2, 3, 4, 5, 6. That doesn't include this group, but what you want to do is include the group. So 1, 2, 3, 4, 5, 6 is your longest chain. Okay. The ketone comes off number 2. That's the smallest number. So 2. So it's going to be 1, 2, 3, 4, 5, 6. So it's going to be a 2-hexone. So it's either this one, or this one, A, B, or D. Has ethyl coming off of number 3 and a methyl coming off of number 4. So it's going to be 3 ethyl, 4 methyl, hexa 2-one. Okay, so coming off of 2, so it's 1, 2, 3, 4, 5, 6. Carbonyl coming off of number 2, so it's got to be A, C, or D. Has ethyl and a methyl. The ethyl coming off of number 3, methyl coming off of number 4. Okay, so so it's either be A or C. We do alphabetical, so it's going to be 3 ethyl, 4 methyl. Not 4 ethyl, 3 ethyl. Okay, reactions of aldehydes and ketones. So what you can do is that you can, because this is a pi bond, you can destabilize it and add across it by adding hydrogenation or reduction. Remember, anytime you add hydrogen, you're reducing or hydrogenating it, and so you can get both these cases. So you can turn an aldehyde into alcohol, or aldehyde into ketone alcohol. We saw the reverse reactions. We took a primary. This is a primary alcohol. It has, this carbon has one attached to it. And then what we did is that when we oxidize it, remove the H, we formed an aldehyde. And we saw this reaction before, where we took a secondary alcohol. So this carbon has 2 carbons, and when you oxidize it, when you take away 2 hydrogens here, you end up with a ketone. So you can do the reverse reactions as well. Right. The other set, carboxylic acids and esters. Okay, so what's common between carboxylic acids and esters is they have a carbonyl group and an oxygen. Okay, if it's a carboxyl group, this oxygen will have an H at the end. If it's ester group, it'll have a carbon group. So just like with the alcohols having ester, and the aldehydes having a ketone, the carboxylic acids have an ester. Right, naming carboxylic acids. So the endings would be oic acid. All right, so for instance, and often we could draw it as a O, this double bond, we'll write it as COOH or CO2H, in the condensed form. Okay, and this guy here, CH3COOH, is ethanoic acid, which has a special name called acetic acid. So it's two carbons, ethane, so it's acid because it has a COOH, so oic acid. Here's structure. So what you do is find the longest chain, 1, 2, 3, 4, okay? So it's 4 carbons, so it's a butane, and it has this attached to its butanoic acid. And you'll number it from where the end is, right here, always at this end. So this 1, so it has a methyl group coming off of number 2 and off of number 3. So it's 2,3-dimethylbutanoic acid. Okay, naming carboxylic acids. So this is a special case of a carboxylic acid. It's a benzene with a carboxylic, and it's called benzoic acid. This one is propanoic acid. It has 3 carbons with a carboxyl at the end, so it's going to be propanoic acid. All right, naming esters. Okay, now these take a little bit more complicated. So what you got to do is you have to break it up into 2 parts. An ester always has 2 parts. It has a part that looks like carboxylic acid, and then it has like an alkane part. And so what you're going to do is you're going to name both parts. So it has 1, 2, 3. So this look like a propanoic acid, but because doesn't have the H on it, we're going to call it propanate. So this is the propanate part, and this is ethyl. So the way that you name is ethyl propanate. So what you do is you look for the 2 parts. You look for the carboxylic acid part, and then you look for the alkane part, or the alkyl part. Okay, so let's name this guy. All right, so that's 1. So we're going to break it up into 2 parts. So here's 1 part, and this is the other part. So it has a propyl on it, 1, 2, 3. So it's going to be propyl something. It says 1, 2, 3, 4, 5. So this is going to be a pentanoic acid. Almost, but there's also it has a methyl coming off of this chain, so it's 1, 2, 3, 4. So if you name this guy, it's going to be 4-methyl propan. 1, 2, 3, 4. Okay, 1, 2, 3, 4, 5. So this is going to be a pentanate. Okay, and it has a methyl coming off of number 4. So it's going to be 4-pentanate. All right, 4-methylpentanate. So you combine them. So you have your propyl, 4-methylpentanate. So you break them up, find the name of the carboxylic group, and then the alkyl group. Okay, so this is propyl, and this is going to be a pentanate with methyl coming off of number 4. 1, 2, 3, 4. Right, so what is the name of this one right here? Okay. What is the correct name for the product of when it's oxidized? So we'll give it to, so it's 1, 2, 3, 4. So it's going to be a butanoic acid, and it's going to have a methyl coming off of number 3. It's going to be 3-methyl butanoic acid. 3-methyl butanoic acid. Okay, you could either this number A or number D. Okay. All right. Okay, the reason why we call them acids is because, like we learned at the beginning of the semester, acid is when a substance can lose an H+. And that's what carboxylic acids can do. They can lose an H+ and form conjugate base. Okay. And, all right. All right, now formation of esters. So how do you form an ester? Well, so what you're going to do is you take a carboxylic acid plus an alcohol. And what's going to happen is the OH of the alcohol is going to pop off, and the H on the carboxylic acid is going to pop off, and they're going to form water, and then these are going to connect. So you have this part, it's going to connect with this part. So you get this thing right here. I don't know why it has this Cl here. That should be it. Okay. What's going on there? Okay, this should be an oxygen right here. Okay. So this, just get rid of this H here. This should be the oxygen right here. Not this HCl. So this should be an oxygen. So you have this 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And there should be oxygen between here and here. Sorry about that. There should be oxygen right here. And actually this is on the wrong spot. This is totally messed up. 1, 2, 3, 4, 5. 1, 2, 3. 1, 2, 3, 4, 5. No, actually, sorry. This guy should be right here, and an O should be right here. Now I'll fix it after I'm done with it, and it'll be you'll see it on the non-narrated version of it. But there should be this LH should be missing, and this should be over here. So this whole thing right here should be this, and there should be an O here, and that's okay. I'll fix that. Okay, that's a mess. All right, making soap. Okay, to make soap, what you can do is you can take an ester, all right, or a carboxylic acid, and you can add hydroxide. And what happens is the hydroxide will break that bond there, and it'll form this substance here. Now, what happens here is this end here loses the H, and it gets a negative charge, and this is a soap molecule right here. And we won't be talking about how soap works, but it's called saponification, which means making soap. So if you add hydroxide in the presence of a carboxylic acid or ester, you can form a soap molecule. Okay, so name the ester formed by adding methanol to a hexanoic acid. So the methanol is going to give the hydroxide is going to, the hydroxide was going to come off. So this is just end up being methyl. So meth is going to be methyl, and the hexanoic acid is going to become hexanate. So it's going to be methyl hexanate. Okay. I don't care which one you pick, B or C. Okay. Another functional group is our carbons with ammonias attached to them. A carbon with ammonia attached is called an amine. So this is an amine. Okay, it's basically a nitrogen with carbons attached to it instead of hydrogens. And amines are weak bases. Okay, that means they can absorb hydrogens fairly easy, and they can react with acids. So anytime you see an amine, think base, and whenever you see a carboxylic acid, think acid. Okay, amides. Okay, amides are amines, so they have a carboxylic acid attached to them. So they're kind of like esters. Esters had, this would be an alcohol, and this would be carboxylic acid. For amide, you have a carboxylic acid and an amine. Okay, and so look for this group here, the carbonyl with the amine. So you have an amide, so it's 3 carbons, so it's going to be propanamide. Okay. This one, here's your amide, and the longest chain is 1, 2, 3, 4, 5, 6. So it's going to be a hexamide. And it has the ethyl coming off number 4, so it's going to be 4-ethyl hexamide. Okay, how you make an amide? It's fairly simple. It's like making an ester, but instead of adding a carboxylic acid and alcohol, you're adding carboxylic acid and amine. And what happens is the amine attaches to the carboxylic acid, and you get this. Okay, so again, just like when you form the ester, you make water. When you form amide, you form water as well. And you can do the reverse reaction, add water, and you can break that bond, and you can end up back with your amine. Okay. Okay, so this is a real common amide. In fact, it was the first organic chemical ever discovered in terms of its chemical formula and synthesis. It's called urea, and is found in your urine. That's why it's called urine urea. And one of the functions of urea is to carry broken down protein out of your body. Proteins have amines in them, and so urea can carry 2 of the amines of broken down. Proteins are made of amino acids. Amino acids have amines on them, and when a protein breaks down, it loses the amines, and the amines get your body needs to get rid of them because they can be very dangerous in your body, and so your body will get rid of them through urea. So we'll add 2 of the amines to a carbon, an amide group, and then this substance is is sent out of your urine. Now, one of the things is that once it gets sent out into your urine, and after you go to the bathroom, um, if you let it sit, what's going to happen is that it eventually is going to be broken down into ammonia and carbon dioxide, and you might have smelled ammonia around after you had that good old stuff of urine sit around for a while. Okay, and that's because is this broken down proteins have released their amines into urea, and urea gets extruded out of your body, and then eventually it gets broken down to ammonia. Okay. All right. Amides. All right. So because of this double bond, we learn about double bonds moving around. So what you can do is you can get a resonance structure for amides, and they can become I don't know, both reactive and fairly neutral because of this. So they can either give up H's or take H's because the positive and negative can move back and forth between these. All right, what is the correct name for the molecule shown below? All right. Okay, so this is going to be amide. Okay, and what you want to do is find the longest chain, 1, 2, 3, 4, 5, 6. So it's going to be all 1, 2, no, 1, 2, 3, A, B, or C. You will number it from this end. So 1, 2, 3, 4, 5. So it's going to be a 4,5-dimethyl. Okay, so 4,5-dimethylhexylamine. Amide. Okay, A. All right, organic polymers. Okay, so one of the things you can do with organic molecules is you can make very, very, very long molecules using a repeating unit. Okay, and these become macromolecules. They call them polymers because poly means many, and they're made out of a basic group called a mer, or it's like a body. Mer means body, so many bodies. And so what you can do, if, like polypropylene, it starts out with a propylene. So this is propylene right here. So propyl has, so this is 3 carbons and it has a double bond, so it's propylene. And then what you can do is attach many, many of these guys together, and then you can form polypropylene. Okay, and so a lot of our plastics are going to be organic polymers, or they're going to be, if you ever hear the word polymer, it's because you start out with a simple unit, and you combine them all together, do a chain reaction, and you get these long chains of synthetic organic polymers. So you have a repeating unit called a monomer, and a previous example is a propylene. And there's a reaction that creates a polymer. It's called polymerization. So what you do is you take the one monomer, mono body, one body, and then you add many bodies to it. And it's fairly simple chemical reaction. What you do is you knock off, you leave one electron exposed. And that one electron becomes very reactive. And then you have a double bond, and that double bond, and that one electron is going to try to connect with this double bond here, and it's going to form a bond, and then it's going to keep growing, and it's called a chain growth. Okay, and you basically can keep this reaction going on and on and on and on until you you can terminate with a real simple, like add acid to it, and you could make this as long as you want or as short as you want by determining where you shut it off. And then you can have, and then there's all kinds of things with these. You can cross-link them, have one polymer connect with the other polymer by adding cross-links, and there's a whole giant science to this. It's pretty cool stuff. So here's some common polymers and their monomers. Probably heard of these guys, okay. Teflon, so you start out with this guy, and then you keep on adding more to them. And these are basically kind of like the plastic sciences, okay. Okay, polyvinyl chloride, all right. So this is the basic monomer here. And what you do is just add more and more through a chain reaction. Okay. And so this short gives you a kind of idea on it. I don't want to go through it. But so this is to make nylon. All right. So nylon is a copolymer, two different molecules combined. So what you do is you add this guy, and then you have this one, and then you add more and more of them together, and you get nylon. All right. So, and it's called condensation because water is being released. Okay. You know, when you condense when you say when water forms on something, it's called condense. Well, this is chemical condensation versus physical condensation, where water is removed and it basically comes out, precipitates out. Physical condensation would be like if you had a cold pipe in the presence of warm air, the cold pipe would water would condense on the cold pipe out of the warm air. And here's another one, dacron. And then, like I said, you can take these guys and then you can cross link them, and you can have them twisted. You can actually have them all straight. There's all kinds of things you can have them form straight, crystalline structure. You can have them all make like wool. You can make them very fine, like in seat covers and so forth. So, and it's how you. So you can make the polymers, and then what you can do is how you make the polymers interact with each other. You can get different kinds of fining of them. All right, so there you go. So they have strong Lund dispersion forces because there's a lot of carbons between them. So they're very strong. So like plastic bags and so forth. They're plastics. So this is just general idea of plastics and how they make plastics. It's interesting. All right, now it's a brief of biological molecules. Okay, so you have carbohydrates, proteins, nucleic acids, and lipids. So carbohydrates are sugars. What we know is sugars. What makes them sugars? I mean, one way you can know if you have a carbohydrate, it usually ends in OSE, OS. And one of the most important carbohydrates out there is glucose. It is a monosaccharide, and there's several other monosaccharides, but glucose is the most important one in terms of us. And you can take glucoses and connect them together to form long chains like polymers. And those can be like cellulose, starch, or glycogen. If you take two sucroses and add them together, you can form these sucrose is a monosaccharide, and then you can take two of them, combine them, and you can take two monosaccharides. In this case, you take a glucose and a fructose. Both are monosaccharides. You add them together, and you would form this thing called sucrose, which is a disaccharide. Sucrose is table sugar. Okay, and you can take a disaccharide like this guy right here. This guy here is a what is this? This is lactose. You don't have to know that, but this is a disaccharide. if you add water, you can break it apart into its monosaccharides. And there's polysaccharides, which are many monosaccharides tied together. And the common ones are starch, which are found in plants. Okay. And there's two kinds of starch. There's amylose and amylopectin. And there's cellulose, which is a really long chain. We can break apart starch in our diet, but we can't break apart cellulose. Okay. Now there's another really important polysaccharide called glycogen, which is our way of storing glucose, which is quite a bit like starch. Okay, another biological macromolecule, which again are part of organic chemistry because it has lots of carbons, are lipids. And lipids are insoluble in water. So natural organic compounds that are insoluble are called lipids. And there are two kinds of lipids. There's fatty acids and there's steroids. And this is a case of a steroid. One way you can tell that it's a lipid is it has lots of carbons and hardly any oxygens. The ratio of carbons is really high, and therefore this is very hydrophobic. Another kind of lipid is our fatty acids or triglycerides. Okay, they don't look like cholesterol, which is a steroid, but they still are very hydrophobic because they have lots of carbons and stands for like between 10 and 20 carbons. Again, lots of carbons means hydrophobic. This is called triacylglycerol, otherwise known as triglyceride. And here's some fatty acids. Okay, long chain carboxylic acids. Skip over that. Triglycerides. Well, our body breaks triglycerides. So a triglyceride is made out of two parts: fatty acids and glycerol. There are 3 fatty acids attached to 1 glycerol. When we eat triglycerides, which are basically like fats and oils, animal fats and vegetable oils, our body will break up the fatty acids from the glycerol, and the fatty acids can be used for energy. Another thing you can do with triglyceride is you can especially so there are unsaturated and saturated fatty acids. Saturated fatty acids are fatty acids that have lots of carbon, single bonded carbons in them. So a fatty acid is a long chain long chain carboxylic acid. And you can have 2 types. You can have where all the carbons are single bonded, or you can have it where some are double bonded. And that's called unsaturated fatty acid. The saturated fatty acids, are usually solids at room temperature, and we find those in animals, like animal fats. Unsaturated fatty acids are liquids at room temperature, and they're called oils, like vegetable oils. Now you can turn an unsaturated fatty acid into a saturated fatty acid by removing a double bond, by adding hydrogens. So what you can do is you can take vegetable oil, which is a liquid, you can hydrogenate it, Okay, so vegetable oils are made of unsaturated fatty acids. When you hydrogenate it, it can turn it into a saturated fat, which is solid. So this is how they make margarine in like Crisco. They take vegetable oil, which has a lot of double bonds in the carbons. They remove the double bonds by hydrogenating, and they make saturated fatty acid, which is solid. All right, don't want to go over soaps, but there you go. So you can just take a look at these. I'm not going to go over them. I'd like to end this soon. It's been a long one. And if you've taken biology, you might have seen this before. And then you have proteins. Proteins are made of amino acids. They're a long chain of amino acids. And proteins have all kinds of functions. They're very, very interesting. I spent 10 years of my life, at least, studying structures of proteins and how they're built and their function and structure. Okay, so this is an amino acid. If you notice, it has an amine and has a carboxylic acid. So the reason why it's called an amino acid is because it has an amine and a carboxylic acid. So protein has many, many, many of these guys all linked together. Sort of like the polymers that we talked about earlier, with like nylon and so forth. These basically the same idea. There's 20 different amino acids. Here's two of them, and here's two more. So there's 16 more. And when you take biochemistry, you'll learn about it. And like I said, you can take two amino acids and link them together. And this is actually a common reaction. What you do is you take an amine, amino acid and other amino acids, and this is just like forming an amide. You knock off the water, and then you connect. Then you end up with this thing right here, which this is an amide. Okay, so when you take so in the formation of a protein, actually a protein is many amides connected together, amides, and so forth. And then we have nucleic acids. Just nucleic acids are made out of three parts. Nucleic acids are made of nucleotides. So the building block of nucleic acids are nucleotides. A nucleotide has three parts. It has a base, it has a sugar, and it has a phosphate. The base is called a base because it has amines in it, N's. It has sugars, and then it has phosphate. So this is one building block. It's called a G. This is another building block, T. Another one's A and C. Okay, and then they have their links between their together. And these two are genes and who we are. So the sugars. So there are two different kinds of sugars and nucleic acids. There's riboses and deoxyribose, and that's where the name like deoxyribonucleic acid comes from, the sugar, and ribonucleic acid RNA comes from this sugar. And then you can bind them together and form long chains. Get your double helix, which is really cool. Wish you could talk more about it, but someday hopefully you'll learn if you want, because it's really cool stuff. Then you form a replication DNA, and that's cool. And we're nearing the end, and I'm about done. And so there's a lot of stuff here. So my guess is I'm going to try to have like a multiple choice test on this. I don't think there'll be any kind of worksheet on it. Uh, I don't know how exactly I'll have you do it. Maybe I'll just let you have this is your resource, and then you can use this during the test to come to figure out your answers. Um, so this basically a synopsis of really the big world of organic chemistry. There's a lot involved with it, and maybe it gave you a little bit of idea of what it gets into. If you take organic chemistry, you'll get a better idea, and then from organic chemistry, you may want to get into biochemistry, or you might want to go into things like plastics or etc. So there's a lot of different options that organic chemistry can lead to. If you the petroleum company, petroleum is oil and gasoline, which are all hydrocarbons. When they make gasoline, there's gasoline is not just one simple chemical, all right, molecule, and it's actually many different kinds of molecules, and how to design the right kind of gasoline is actually a lot of very interesting work. You may have heard of these new kinds of synthetic oils for your car, where they take natural gas and turn it, and they have your oil for your motor oil made on natural gas. So they take methane and ethane somehow, and they combine them together to form long chains of molecules. And doing that, they can be very exact in how they design these molecules. And so, what makes oil so slippery? I mean, there's all kinds of things to think about when we do these kinds of things. All right. So I think that's about it. There might be a couple left, but so we'll end it here, and I'll send this out. And the next day with on how maybe we'll split it up. Let's do like a half hour a day or something, so I don't bore the heck out of you. And I'll refer to where it is in your book if you have it. Have a book. And okay, so let's see. That might be it. Okay. So this talks about how DNA makes proteins.